In this video, we're going to explore the magnetic force, or in other words, look at what magnets will push and pull. So, as we talked about before, a magnet will exert a force on a magnet, another magnet, right? You're used to that. North pushes on north, south pulls on north, etc. But interestingly, it will also produce a force on a moving charged particle. And we'll talk more about this in another video, but this is because moving charges can create a magnetic field. And so if those moving charges create a magnetic field, then that means there's this aspect of magnetism to them, and therefore they will be, interact with the magnet as if they were a magnet. So the way that we measure this, we're actually only going to talk about the force on a charged particle, a moving charged particle, and that's going to be measured by F equals Q V B sine theta. And I'm mostly introducing this. I don't think we'll actually do a lot of calculations with this, but I want you to have seen this before. So Q, this is, as we've seen before, the charge, which is measured in coulombs. V is the velocity of the particle. B is the magnetic field. Measured in Tesla. And theta is the angle between the field and velocity. So you'll notice that this is greatest when the field and velocity are perpendicular. So if the field is pointed this way and the velocity is pointed up, then that's a 90-degree angle between them, and sine 90 is 1. Any other angle that they're at will have a smaller value up until, if they're pointed in the same direction, sine of 0 or sine of 180 if they're in opposite directions is 0. So that's the part I really want you to pick up on here, not worry so much about the calculation, but the idea that if they're perpendicular, you get the most force. If they're parallel, you get 0 force. So now how does this work? Because we just said before that was the magnitude, so we also need to know the direction of the force. And this uses what we call a right-hand rule. So you will have to use your right hand for this. You can't use your left. Well, you can use your left hand, but you got to do it differently. But we always use right-hand rules for math because of how we've set up our math systems to give us consistent answers. Whoops. So what we have here, if, for example, we've got a magnetic field that's pointed like this. So this is my magnetic field, pointed straight downwards. And if I have a charged particle that's moving through like this, you notice they're perpendicular. So because they're perpendicular, we're going to get the most force out of it. So now what I want you to do is take your right hand, and what you do with this is you point your fingers in the same direction as the velocity. So I guess for you, if I'm thinking about the screen, it's going to look like this. For me, watching the screen, I'm pointing like this, but point your fingers in the direction of the velocity, and then curl them towards the shortest distance towards B. So B is pointed downwards, V is pointed to the side. So if you point your fingers along V and then bend them the natural way to bend them, the smallest angle towards B, then whatever direction your thumb points, that's the direction that the force will act. So in this case, what you'll notice is so let me make sure I get this right. Fingers towards V, point down. What you should see is your hand, if you copy this here, your thumb will be pointed in towards your screen. because you'll point your fingers off to the right. You'll bend them down. The only way to bend them down nicely is with your thumb pointed inwards towards the screen. And so that's the direction that you would expect to see the particle experience a force. It will be pushed inwards, so inwards, kind of back in towards the screen. So towards me, if you want to think about it that way from that perspective. This one's a little weird to do kind of over a video, but if we talk about it in person, I think it'll track pretty clearly if you get a little confused. So let me know if you have questions about that, but otherwise you can kind of jump forward.